A greenfield project starts with a patch of untouched, empty earth. From that blank slate, we have to build a fully functioning industrial facility right from the ground up. Think about the coordination required to set up a smart thermostat and a few connected lights in your house. Now, imagine scaling that effort up to manage an entire automated plant with miles of piping and thousands of sensors. When you have thousands of specialists from different engineering fields all trying to work on the same site at once, the biggest risk to the schedule isn't a lack of individual talent. It is the friction that happens when those different teams stop talking to each other. To keep everyone moving together, management relies on a few specific tools. The first is a Gantt chart. This timeline tracks individual tasks, showing us exactly when one job needs to finish so the next can begin. We track momentum using an S-curve. It starts slow in planning, climbs steeply during construction, and levels out at final handover. By adding markers, we measure cumulative progress, showing if the money spent matches the physical building getting done. Keeping those two things, the money spent and the bricks laid, moving in perfect step is the ultimate goal. In the industry, we call this protecting the S-curve. This graphic shows the S-curve laid over the task schedule, which gives top management an immediate health check. A quick glance at that curve tells them if a project is burning through cash faster than it is building physical reality. Before anyone buys a single piece of equipment, we need a plan. It starts with the process flow diagram, or PFD. This is a flowchart showing how liquids and gases will move through the plant. From there, we move to the piping and instrumentation diagram, or P&ID. If the flowchart is the rough sketch, this is the master blueprint. This diagram shows every single pipe, valve, and sensor. As you can see highlighted here, the rule is absolute. If a component is not explicitly drawn on this P&ID, it does not get purchased, built, or installed. It serves as the central truth for the project. Plumbers, electricians, and software engineers all read this exact same map to stay aligned. A master blueprint tells us we need a valve in a specific spot, but it doesn't tell us exactly which valve to buy out of thousands of available options. To make a purchase, we use instrument data sheets. These highly specific forms serve as the master technical profile for every individual piece of hardware in the plant. Let's examine this data sheet. Notice the detailed grade of requirements. Sections like process conditions and sensor element lock in exact global standards for the operating pressures and the specific metal alloys required. Standardizing these details leaves zero room for guesswork. For example, two valves might look identical on the outside, but the data sheet ensures a vendor doesn't accidentally supply a basic water valve when the system actually requires one built to resist highly corrosive acid. By strictly following these documents, project managers can safely execute million-dollar orders, knowing they are preventing mistakes that lead to dangerous leaks or massive construction delays. Even with perfect blueprints and data sheets, delays happen, but they rarely happen deep within a single department. They happen at the seams, the vulnerable handover points where different engineering departments meet. A prime example is the handoff for safety systems. First, the process engineering team creates the ask. Their job is to map out the physical chemical processes and spot the risks. They run a study called a HAZOP, which is a structured way to ask what if. What if a pipe clogs? What if the pressure climbs too high? Now, those safety questions need a technical response from the instrumentation and control team, the group in charge of sensors and automation. Looking at this graphic, we see how the ask crosses the seam so they can build the answer. So if the process team asks, what if the storage tank overpressurizes? The control team writes a rule into the system. If tank pressure hits the red zone, automatically snap the main intake valve shut. Project managers have to actively watch these collaborative handoffs. Managing those seams is how a team turns a theoretical safety study into a real, functioning physical safeguard. Bringing a massive piece of land to life requires mastering a few strict rules. First, you have to master the documents. Your diagrams and data sheets are the unbreakable laws of the site. Second, you must govern the handoffs. Pay close attention to the seams where different expert teams overlap. And as we see on this summary slide, the third rule is to protect your S-curve. By relying on rigorous global standards instead of custom engineering, you keep your schedule and costs perfectly tethered to your physical progress. Internalize these three pillars, and you take the chaos out of construction. you will have the framework needed to build safely, execute precisely, and bring